So inverse functions are functions, if you have two functions and they are inverses of each other, then what that means is we can compose them with each other and it will return just x. So I could plug f of x into g of x and it'll simplify to x, or I could plug g of x into f of x and it will simplify to x. So the reason we're talking about inverse functions is because all the equations we've looked at so far in this section have been exponential, right? But a logarithmic function is the inverse of an exponential function. So one of the things that's really useful is it gives us an algebra tool if we want to solve for one of those functions. So the way that we talk about logs is the most common base is base 10. So every calculator has a log button and it is assumed it is log base 10. So if I plug 10 to the x into log, it just simplifies to x. If I take 10 and raise it by log x, it will simplify to x. So that is this property in action. If f of x equals 10 to the x and g of x is log of x, that's what we've got here. So this is g of f of x. So I composed it. I took f of x and plugged it into g of x. This next one is saying, well, I took g of x and plugged it into f of x. If you take log of b, it equals x. If log of b equals x, then that implies that 10 to the x equals b. So if we take the base and raise it over the x, it switches the x and y values. So the thing that goes in is now the output, and the thing that came out is now the input. The natural log has the same properties, except its base e. So that means for natural log, f of x is e to the x, and g of x is natural log of x. So every calculator has a natural log of x button as well. So to see this in action, let's actually look at an example. So if we wanted to solve this function for t, okay, as of now what we would do is we would put this in y1 in our calculator, put this in y2 in our calculator, and find the intersection. But what's actually happening here, if we take this function and I divide both sides by 30, I get e to the 0.25t equals 4. So now, to get this t out of the exponent, I can compose it with its inverse, or I can take the natural log of both sides. So the natural log of e to the 0.25t equals the natural log of 4. The natural log wipes out the e, and I get 0.25t equals the natural log of 4. Now to solve for t, I just divide both sides by 0.25, and this is about 5.55. So if I graph these two sides of the equation in my calculator and looked for the intersection, that would be approximately the intersection. So what is the growth rate and continuous growth rate of this function? So the growth rate, I can see here that the growth factor, or in this case it's a decay factor since it's less than 1, is 0.9. Oh, I'm sorry, guys. This goes with this. We're still working with this guy. So the growth rate is, the rate is 25%. So R is 0.25, which works out to be 25%. The continuous growth rate is e to the 0.25 minus 1. So it's essentially the effective yield. And you get 0.284, which is approximately 28.4%. I should have put a line here for these two problems. For the next problem, they want us to solve this new equation for t. So for this new guy, we're still going to make the same initial first step and divide both sides by the constant out front. So that leaves me with 0.9 t equals 5. But here I don't really see a base. I don't want to take log base 0.9. That really doesn't make any sense. So I can actually just still take the natural log of both sides to solve. So the natural log of 0.9 to the t will equal the natural log of 5. And there's this really awesome property of logs that says you can take an exponent and pull it down in front of the function. So now I can say t times the natural log of 0.5 or 0.9 equals the natural log of 5. And now to solve for t, I just divide both sides by the natural log of 0.9. These natural logs do not cancel. You would actually have to type in your calculator natural log of 5 divided by the natural log of 0.9. And if you do that, this is approximately negative 15.28. So what is the decay rate? So there is not a continuous decay rate for this problem because the rate does not involve E. So B is 0.9. So in order to get R, it's our rate, our factor B minus 1, and I get negative 0.1, which is negative 10%. So when you're looking at a decay function in this form, the B value inside is telling you how much you're keeping every increment of time. So we're retaining 90%, which means we're losing 10%. So this rate of negative 10%, you can sometimes just see that in the number.